Welcome back to part 2 for the virtual lecture for TCSS 322 on January 13th. We're going to begin by ending up with the 3 practice problems from section 6.3, and then we're going to go on to 6.4 and look at binomial coefficients and identities using combinatorial proof. Well, let's see how you did. So for part 1a, how many bit strings of length 12 have exactly 5 zeros? I think this is an interesting problem because what we're looking at here is an ordered arrangement of the bits 0 and 1. The problem is the 5 zeros aren't distinct, they're all the same. So in some sense we're looking at the set of positions where the zeros lie as opposed to the order in which we're putting the zeros down. To do this counting, we want to pick the locations for the zeros. Since there are 12 locations and I need to pick 5 of them, this can be done in C, the combinations of 12 things taken 5 at a time, the C of 12, 5 ways. As an example, if you pick your ways, let me start with, suppose my 5 set looks like 1, 5, 6, 10, and 12. Those are the positions where I place zeros. The result is to put 1s everywhere else. That gives me one possible string with exactly 5 zeros, and every subset of 5 positions will give me a different string. So the answer to part 1a is simply the combinations of 12 things taken 5 at a time. For part B, we ask for how many bit strings have more zeros than 1s. Well, you're going to have to break this down into disjoint cases. That means you have either 7 zeros, 8 zeros, 9 zeros, 10 zeros, 11 zeros, or 12 zeros, and each one of those needs to be added separately. So when you have 7 zeros, there are C of 12, 7 ways to do it. You add on to that the number of ways to have 8 zeros, 9 zeros, and so on until you get to 12 zeros. Oh, looks like I skipped 10 zeros in there. Okay? So it's the sum of the combinations of 12 things taken 7 at a time, 8 at a time, 9 at a time, all the way up to 12 at a time. For part 1c, we want to know how many bit strings have at least 10 ones. This is really no different than what we just did before, except rather than picking the position for the zeros, we want to pick the positions for the ones. So we will add on to that the combinations of 12 things taken 10 at a time, 11 at a time, and 12 at a time. How about the bit strings of length 12 that have at least 3 zeros? Well, we could break them into disjoint cases, adding up 3 zeros, 4 zeros, 5 zeros, 6 zeros, 7 zeros, all the way up to 12. That's going to be a lot of writing. The other way to do it is to sort of take the complementary event and subtract it. We can take the total number of bit strings, which is, you have 2 choices for each position, so that's going to be 2 to the 12th, and subtract off the number of strings with at most 2 zeros. Because if you remove everything that has 2 or fewer zeros, you're only left with the strings that have 3 or more. And it's slightly fewer terms, so you'll get the total number of strings, which is 2 to the 12th, and then you have to subtract off the strings with no zeros, with 1 zero, and with 2 zeros, and that will give you your answer. For question 2, we have a different kind of approach. We want to know how many ways are there for 10 women and 6 men to stand in a line so that no 2 men stand next to each other. I approach this problem by first arranging the women. So task 1 is to arrange the women in a line, and there are 10 factorial ways to do that. Let me draw a picture. Let's pretend the women are in line. Then we need to understand that the men can be placed in the front of the line, in between any 2 women, or at the end of the line. So let me select the positions that the men can stand in. And notice if we look at the places that they can go, there are 11 total places. Let's pick the places for the men to stand. So there are 11 places we can choose from, and we have to choose 6 of them. So there are 11, choose 6. And then after we've picked where the men are going to stand, then we actually have to order the men in those positions, and that can be done in 6 factorial ways. So the answer here is going to be 10 factorial times 6 factorial times the combination of 11 things taken 6 at a time. For the final question, I'm going to go to the next page, and we're going to put the same arrangement of men and women around a circular table. The difference with a circular table is a rotation of a seating arrangement is considered equivalent. So we don't want those to be counted as different arrangements. And as an example, if I have just 3 people around a table, A, B, and C, rotating that 120 degrees, giving me the arrangement C, A, B, rotating 120 again, giving me the arrangement B, C, A. Because this is a circular table, those arrangements are considered the same because the neighbors of A, regardless of which arrangement you're looking at, are exactly the same. A has B to the left and C to the right each time. So it's a different example of cow counting coming into play here. So task 1 is to seat the women around the table. We can pretend by putting them in the table in 10 factorial ways, but then any rotation of the table will give us an equivalent arrangement. There are 10 possible rotations, so the number of ways to seat the women around the table is going to be 10 factorial divided by 10, which is a total of 9 factorial ways. Again, we want to select the positions for the men to sit, and this time, because it's circular, there isn't a beginning and an ending spot, and there only end up being 10 different positions that are available. We need to select 6 of them, so we end up with the combinations of 10 things taken 6 at a time for the number of positions that our men can sit in, and once you've selected those 6 positions, you have to order the men in them, and there will be 6 factorial ways to do that. So the answer for sitting 10 women and 6 men around the table so that no men sit next to each other is the product 9 factorial times 6 factorial times 10 choose 6.